Welcome to the companion video for Statistical Reasoning Part 1. Through those notes, we got a basic idea of statistics, and these notes are going to go through some example problems to help build upon your quantitative reasoning skills as required for this course. Because be aware, this course is not going to make you perfect with statistics. You have to take some statistics courses to go deeper, spend an entire semester on that. And some of you may have already done that. This is just a slight review for you. So these problems will just give you an idea of a little bit more application of this, and then we'll be going deeper when we hit the After Scientific Method Part 3 notes. When we're dealing with the analysis phase that comes after experiments, where you've collected your empirical evidence and you want to analyze it to decide if you should accept or reject your hypothesis from there. And as always, I like to start with a little video review, and the Crash Course series here has done an excellent job of presenting this. And it kind of gives you a summary of what I've talked about before in the previous notes and some extra context and examples.
Hi, I'm Adrienne Hill. Welcome to Crash Course Statistics. We spent a lot of time talking about data visualization and different kinds of frequency plots, like dot plots and histograms. They tell us how frequently things occur in the data we actually have. But so far in this series, the data we've talked about isn't all the data that exists. If I want to know about student loan debt in America, I'm definitely not going to ask over 300 million Americans. I'm just lazy like that. But maybe I can find the time to ask 2,000 of them. Samples and the shapes they give us are shadows of what all the data would look like. We collect samples because we think they'll give us a glimpse of the bigger picture. They'll tell us something about the shape of all the data, because it turns out we can learn almost everything we need to know about data from its shape. Picture a histogram of every single person's height. Now imagine the bars getting thinner and thinner and thinner as the bins get smaller and smaller and smaller, till they're so thin that the outline of our histogram looks like a smooth line, since this is a distribution of continuous numbers, and there's an infinite possibility of heights. I am 1.67642 and on meters tall. If we let our bars be infinitely small, we get a smooth curve, also known as the distribution of data. A distribution represents all possible values for a set of data, and how often those values occur. Distributions can also be discrete, like the number of countries people have visited. That means they can only have a few set values that they can take on. These distributions look a lot more like the histograms we're used to seeing. Like a histogram, the distribution tells us about the shape and spread of data. We can think of distributions as a set of instructions for a machine that generates random numbers. Let's say it generates the numbers of leaves on a tree. You may be wondering why we have a tree leaf number generating machine. The idea here is that everything can generate data. It's not just mechanical stuff. It's leaves and animals and even people. The distribution is what specifies how the knobs and dials on our machine are set. Once the machine is set, every time there's a new tree, the machine pops out a random number of leaves from the distribution. It won't be the same number each time though. That's because it's a random selection based on the information the knobs and dials tell us about our distribution of leaves. When we look at samples of data generated by our leaf machine, we're trying to guess the shape of the distribution and how that machine's knobs and dials are set. But remember, samples of data are not all the data. So when we compare the shapes of two samples of data, we're really asking whether the same distribution, these machine settings, could have produced these two different but sort of similar shapes. If you got an especially expensive electricity bill last month, you might want to look at the histogram of your average daily energy consumption this month and the same month last year. Check them out side by side. It's not that realistic to expect that you consumed energy at exactly the same rate this month as you did the year before. There are probably going to be some differences. But your question is whether there's enough difference to conclude that your energy consuming behaviors have changed. When we think about data samples as being just some of the data made using a certain distribution shape, it helps us compare samples in a more meaningful way. Because we know that the samples approximate some theoretical shape, we can draw connections between the sample and the theoretical machine that generated it, which is what we really care about. Well, data come in all sorts of shapes, let's take a look at a few of the most common, starting with the normal distribution. We mentioned the normal distribution when we talked about the different ways to measure the center of data, since the mean, median, and mode of a normal distribution are the same. This tells us that the distribution is symmetric, meaning you could fold it in half, and those halves would be the same, and that it's unimodal, meaning there's only one peak. The shape of a normal distribution is set by two familiar statistics, the mean and the standard deviation. The mean tells us where the center of the distribution is. The standard deviation tells us how thin or squished the normal distribution is. Since the standard deviation is the average distance between any point and the mean, the smaller it is, the closer all the data will be to the mean. We'll have a skinnier normal distribution. Most of the data in the normal distribution, about 68%, is within one standard deviation of the mean on either side. Just like the quartiles in a box plot, the smaller the range that 68% of the data has to occupy, the more squished it gets. Speaking of box plots, here's what the box plot for normally distributed data looks like. The two halves of our box are exactly the same because the normal distribution is symmetric. You've probably seen the normal distribution in a lot of different places. It gets called a bell curve sometimes. Attributes like IQ and the amount of Fruit Loops you get in a box are approximately normally distributed. Normal distributions come up a lot when we look at groups of things, like the total value rolled after 10 dice rolls or birth weights. We'll talk more about why the normal distribution is so useful in the future. As we've seen in this series, data isn't always normal or symmetric. Oftentimes, it has some extreme values on one side, making it a little bit skewed. Age at death during the Middle Ages is left skewed, because lots of people died young, while the time it takes to fill out the Nerd survey was right skewed, because some people lollygagged. In a box plot of data from a skewed distribution, the median will not usually split the box into two even pieces. Instead, the side with the skewed tail will tend to be stretched out, and often we'll see a lot of outliers on that side, just like the box plot of the Nerd survey times. When we see those features in our sample of data, it suggests that the distribution that generated our data also has some kind of skewed tail. Skew can be a useful way to compare data. For example, teachers often look at the distribution of scores on a test to see how difficult the test was. Really hard tests tend to generate skewed scores, with most students doing pretty poorly and a few who still ace it. Say we flash pictures of 20 Pokemon and ask people to name them. Here are their grades. Or another sample from a test asking people to list all 195 countries. We can compare the shapes and centers of these two groups of tests, as well as any other notable features. First of all, these two samples look pretty similar. Both have a right skew, both have a pretty low center, but the second test has a more extreme skew. Bigger skewed tails usually mean that the data, and therefore the distribution, has both a larger range and a bigger standard deviation than data with a smaller tail. The standard deviation is higher because not only are extreme data further away from the mean, they drag the mean toward them, making most of the other points just a little further from the mean too. While the direction of the skew tells you where most of the data is, always on the opposite side of the skewed tail, the extremeness of the skew can help you mentally compare the approximate measures of spread, like range and standard deviation. But we compare the shapes of two samples in order to ask whether the shape of the distributions that generated them are different, or whether one shape could have randomly created both samples. In terms of our machine analogy, we ask whether one machine with its knob settings could have spit out two sets of scores, one that looks like test A and one that looks like test B. Answering that question gets complicated, but we'll get there. Now that we've examined the tails, let's look at the middle of some distributions. Almost all the distributions we've seen so far are unimodal. They have only one peak, but there are many times when data might have two or more peaks. We call it bimodal or multimodal data, and it looks like the back of a camel, or maybe like two of our unimodal distributions pasted side by side. And that's probably what's happening. The unimodal stuff, not the camel thing. Often when you see multimodal data in the world, it's because there are two different machines with two different distributions that are both generating data that's being, for some reason or another, measured together. One possible example of this is the length in minutes that the geyser Old Faithful erupts. Most eruptions last either about 2 minutes or about 4 minutes, with few eruptions around the 3-minute mark, giving us a bimodal distribution. It's entirely possible that there are two different mechanisms behind the data, even though they're being measured together. For example, one set of conditions may lead to an eruption that's about 2 minutes long, and another, maybe a different temperature or latency, leads to a different kind of eruption, which lasts on average 4 minutes. Since these two potentially different types of eruptions are being measured together, the data looks like they come from one distribution with two bumps, but it's likely there's two unimodal distributions being measured at the same time. Another example that you don't need to be a geologist to understand is the race times for some marathons. While this data may look like it comes from a unimodal distribution, in reality there are two big groups of people who run a marathon: those who are competing and those that do it to prove they can do it. There's usually one peak around the time that all the professional runners cross the finish line, and another when the amateurs do. While we don't know for sure that bimodal data is secretly two distributions disguised as one, it's a good reason to look at things more closely. We'll finish today with uniform distribution. Even though we haven't mentioned uniform distributions yet, you've probably come across them in your everyday life. Each value in a uniform distribution has the same frequency, just like each number on a die has exactly the same chance of being rolled. When you need to decide something fairly, like which of your 6 roommates has to do dishes tonight or which friend to take to the Jay-Z concert, the best thing you can do is use something like a die that has a uniform distribution. That gives everyone an equal chance of being picked. And you can have uniform distributions with any number of outcomes. There are 20-sided die. When you're in Vegas playing a round of roulette, the ball is equally likely to land in any of 38 slots. There's a difference between a shape of all the data and the shape of a sample of the data. When we talk about uniform distribution, we're talking about the settings of the data generating machine. It doesn't mean that every sample, or even most samples of our data, will have exactly the same frequency for each outcome. It's entirely possible that rolling a die 60 times results in a sample shape like this, even if we know the theoretical distribution looks like this. Using statistics allows us to take the shape of samples that has some randomness and uncertainty and make a guess about the true distribution that created that sample of data. Statistics is all about making decisions when we're not sure. It allows us to look at the shape of 60 dice rolls and figure out whether we believe the die is fair, or whether the die is loaded, or whether we need to keep rolling. Whether it's finding the true distribution of eruption times at Old Faithful, or showing evidence that a company is discriminating based on age, gender, or race, the shape of data gives us a glimpse into the true nature of what's happening in the world. Thanks for watching, and DFTBA Q. I'll see you next time. Crash Course Statistics is filmed in the Chad and Stacy Emig-Holtz studio in Indianapolis, Indiana. And
Okay, so it's a good review of distributions and why it's really important to understand where is the data clumping, because we've talked about measures of centrality, which is what's the most common thing you're seeing in the measures of spread. And combining the two to see the distribution is, well, where is the majority of our data clumping? Is it lower values, higher values, and which one is considered good? And if we can start seeing that more is happening higher, then maybe that can tell us something. But it depends upon the context that we're looking at versus a skewed distribution and a normal distribution. And remember that, like a normal distribution, we can look and see, okay, well, we can use the mean or the median as the good measure of centrality. And then from there, we can decide upon, okay, well, what's the best way to measure spread? And we can always look at things like range, but if we're looking at standard deviation, which is always tied to the mean, well, and that's good for normal distributions, but when it comes to skewed data, where it's very skewed, well, maybe then we should be turning to our box plots and that interquartile kind of range that we've seen before to help guide us on what is the most central and most common amount of the data and how is it clumping. And these things can definitely then help us when we're comparing two different data sets to see is there any big difference between all of them.
it's made with the help of
So to begin with, I want to do like a little review of if you were given some basic calculations, how could you draw your own box plot? Now for this course, things like the mode, median, mean, and the quartile ranges, I am never going to ask you to have to calculate those yourself. You should understand how they work, you should understand the things that affect them, and that kind of range, and go back to the examples, explain how they're calculated. Most times I'll just give you these calculations, and then you can start backing up your argument. And one good first step to do that is to draw a descriptive statistic diagram that shows this. And when looking at the data, you always remember that things like, okay, well, I've got my min and max, and the Q1, Q3, and median are the most important things you need when drawing your box plot or your box and whisker plot, is that you have your min and max, which are the farthest range. So min is the smallest data value that you have, and max is the largest data value that you actually have. And so when you're looking at these, we're like, okay, well, we probably should start with making a number line. And these are good ways to tell, well, how should I make those number lines? Because, well, with min, you should probably at least start, okay, for my number line, I'm going to start down here, and I make that 0. You could make it any value smaller than 1, doesn't really matter, but as long as values that are smaller than your actual min. And then you have your entire line across, and then you'd be going up to your max, and the same thing, just pick a value larger than your max. I'm just deciding upon 100 here so that we can have an entire number line that covers like the entire range of data values that you would have. From there, then, remember, you start deciding upon, okay, well, I have the min value, which is 1, and then I have the max value, which is 97, and those mark the outliers for what you are working with. From there, you go with your median, and you draw that line. I'm estimating roughly halfway in between. There you have your median for your box. You next then take your Q1. Remember, that's your first quartile, so it's the mid-range, the median between your this center value and your min. That was calculated based upon the actual data, and here the calculation showing that it's 26.25. So if this is roughly 50, I'm going to say this is roughly where this one should follow. We connect it from there, and then we can draw our line. So we have our whisker, the start of our box to the actual median, and then we go to quarter Q3, which is the next quarter, which would be at 64. I'm just guessing. Don't worry, there's a better diagram on the next slide from here, which is the next box, and then we draw the line. And you can see I have no good drawing skills at all when it comes to presentations. But you can see then, well, okay, this is then giving you a visual representation of that actual distribution. And from this one quickly, well, maybe it's a normal distribution. We have to see once we get it drawn betterly, since this isn't super accurate, but it gives you a visual way to start looking at the actual spread of the actual data, seeing well, okay, well, this is 25% of the data, and so forth. This is 25%, and so forth upwards, and saying, okay, well, how does the data spread? Is it skewed? Is it not skewed? Which measure of centrality and spread should I actually use? And where is the data clumping? And what can I draw from this actual data? Here, we don't really have a context. It's just basically randomly generated numbers. You have no context, so it's hard to draw anything more than where along the number line the data is actually clumping. But once we throw in a context, we'll be able to do a lot more. So here, woo, look at that. Way nicer actually, pre-prepared diagram. So this is that same diagram that I was hand drawing quickly, but a little bit more accurate and drawn on here, that you once again have your whiskers, you have your min and your max, you have your Q1, you have your median, and you have your Q3. And remember, this splits it up into 4 sections that we know, okay, from the min value up to Q1, that is 25% of the data points follow within there. So if we had 100 data points, that means that between the min and Q1, 25 of those data points would lie there. It doesn't mean that they're equally distributed across here, it just means they fall within this range. They could be clumping in different areas, but at least we broke it down from here. And then the same thing from Q1 to median, that's another 25 data points or 25%, and same so forth going up. And this allows us to break it up more. Instead of just thinking from the min to the max, that range of 96 values, we can start interpreting more of what's happening. Like with the median tells us that from that point up to the max, then we know, okay, well, 50% of the data points fall between there, and then below it another 50% follow below in here. And then with the quarters here, well, that breaks it down even more. Okay, well, we know this is 50, but okay, well, within this entire range, then we know, okay, there's 25% here, and there's 25% here, and we can start seeing where are things kind of clumping overall. So that's drawing it. Now, another question that I could give you in the future is deciding upon, is the data skewed and how is it skewed, and which measure of centrality would be best used. Now remember, when comparing these, you want to start by looking at the mode, median, and mean and seeing which one is bigger. And if you're finding that the mean is smaller or larger than these other two values by quite a bit, then you're probably hitting upon a point where there's a skew in the actual data. Whereas if they're close to each other, then we're probably sitting at a more normal distribution. And now even looking at this like box and whisker here, we can kind of see, well, okay, the whiskers here look roughly the same size, so do the boxes, and we can see that the mode and mean and median are all basically overlapping. So what we have here is roughly a normal distribution that's not skewed enough, so I would just classify it as a basic normal distribution. Right here. And you can see that even looking, well, okay, the mode equals the median, and the median roughly equals the mean, and the mean roughly equals the mode. From there, there's only that 0.73 off from these two values. So we'd say we have a normal distribution, and so we could use either of the measures of centrality. So we could look even here at mode, we could look at median, or we could look at mean, because they were all generally saying the same value. It just, each one gives us a little bit more data, like looking at the median and the fact that the mean are the same, then we really know, okay, well then 50% of our data falls between the minimum and this value, so 46, and the other 50% falls between max and the median. We'll start telling more of a data from there. For measures of centrality, if we go with the median, well, then we can start working with the Q1 and Q3 and know that these ranges are interquartile range, that we know, okay, well, if each of these sections here, so 1, 2, 3, 4, break up the data into 4 equal kind of chunks, which the ranges can be different, but it's supposed to be that like quarter of the data falls here, quarter of the data falls here, another quarter here, and another quarter here. Well, then we can know, we can look between Q1 to Q3, that's 2 quarters, so from here to here, we have 50% of the data, and then we have the actual median from here. So we can know, well, what is the general measure of centrality, so it's the most common we're seeing, and how far out do a lot of the other points? And if this is 50%, that's a good chunk of your actual data, and can give you an idea, well, how closely or not closely or spread out is that overall data. Boom. So here's another one. So, but this distribution. So again, we want to start looking at the mode, median, and mean. And this is why sometimes it can help to draw this graph out, because you can automatically see all of the actual values. And also the box plot itself is really giving you an indication that this is skewed. And along the number line that we're working with, so smaller to the larger values in that range, it's not sitting right in the middle, being that it would be like nicely distributed and going over that actual data. Instead, we have something where it's clumping all the way over here and not so much on this section there. So we've definitely got some kind of actual skew. And if we were trying to draw this roughly, we can't do this perfectly knowing more data, but we know we have the mode, which would be one peak here, and then the median and the mean. And so this one here probably, based on the data, like spikes up here and then comes down. And so we're seeing that there's more of a clumping on this case. And so we have the mode like being here the kind of peak. We have a lot more data within this case. This is a shorter kind of range, even for 25% of the data here. And you have to think, okay, well, from here to here, that's 50% of the data. And then the other 50% comes over here. So there's a lot of data points that are falling within this smaller range here versus all the way over here. And so we have a skew to this other side. Now, to determine which one it is, because we have either the positive or negative, which also referred to like so positive or negative for the left or the actual right, you want to start comparing again between the mode, median, and mean. And the mean, again, this case here is easy to see is smaller than all the rest of the actual values. And the mean will always point you towards the tail of the actual data and where you're going. So this is going up to larger values being positive and moving to the actual right, versus if it's going down and going to smaller values being negative and moving to the actual left. So the mean is pointing out to the tail. We know that it's smaller than the rest. We know we have this clump, and so mean that this data is skewed going off to the positive or being right. So it's a positive skewed or right skewed. So two terms for the same thing. And what this really helps us to know from the skew here is, well, this is a bigger one. Like, we've got the median and we've got the mean, and they've got difference. Okay, well, we've got 27.50, the mean is 33. That's off by 6. And at a scale of 100, maybe that's not so much, but that mode being at 5 and being off of here by, like, right here is like by almost 28. Roughly, that's too big, and then we're like, hey, we can't use the mean as a measure of centrality. It's not really going to talk about what's most common. Well, closer from here, we can start talking about the mode and the median. And so in this case, probably the median is a better case, and we should take into account the actual mode as being a better clustering. And then if we have the median, then we can use these interquartile ranges to tell us more information. This skew also tells us that we have more data points here going towards the bottom end. So depending upon our context, that can help us make more decisions. So you can see here, again, mode is less than median, is less than mean. I probably screwed that up on the previous ones because I was looking this way, but the mean is the larger one going to the right because it's positively skewed right here. And so you can see, okay, we've got these three values. So I think in the previous slide, I was just talking about more the mean being smaller, but I was not looking properly at the data line, and it's actually a larger value, and the rest of these are going down. And so in that case, where the mean is larger, and then the median, and then the mode are smaller values from right there, where we have a positive skew. And you kind of see that clumping more to the left, the skew goes off to the actual right, and so you have a positive or right skewed actual graph. And we should be using the median and the mode as better measures of centrality, and then using the interquartile range for measures of spread. So we have another one here. I just want to pause for a second. I want you to think, looking at this, what type of skew do you think it would be? Even just looking at, like, okay, well, based upon the number line from 0 to 100, and we can see the median and the interquartile range between Q1 and Q3, where is most of the data actually clumping? Okay, well, boom, pause so you can think, and now I'm back. And, well, you can look here. Okay, well, we've got the mode being a large value, the median being smaller than that, and then the mean being smaller than that. And they're kind of close, like the mean to the mode, not really. Same as the median to the mode. The mean and the median are kind of close, but the fact that this is so skewed off that we have this bigger range here, and then we have right here to right here, and like this is clumping that you're like, no, something seems to be off. And even if we look from the median, remembering up to max, and drawing this way, remember, well, that's 50% of the data points, and this is 50% of the data points fall between those two. You're like, no, like we're clumping more up here in the higher actual values, and then it's way more spread out as we go down here. And so, like, I'd say, yeah, we definitely have a skew, and we can back up that argument more by looking at these three. So if we looked at this data and looking at the mode as a clump and trying to draw it from here, we're probably getting something closer to like this as a distribution. And you can see it's clumping, like more of the data again is clumping up to here and having some kind of peak, not drawn perfectly here. But we know, okay, well, the data, more points, if we're counting to a kind of frequency, are falling within here and saying, well, what's happening? So we can see from here, okay, well, mode is greater than median, is greater than mean, so we have a negatively left skewed, and again, that mean is smaller values than all these three, and it's spreading out, and it's going towards the actual smaller numbers, and so it's skewed to the left or negatively skewed. Again, both same terms. And so now, with this negatively skewed, you have to remember all the clumping data is up on the right side to higher values, and depending where that is, and given a context, again, we can tell more of what's going on. Like if this was test scores for a class, you'd be like, well, a lot of people are getting a lot of higher values in that range of more from 50 up to 80. And maybe the overall class did better. Who knows? So that's where we come back to quantitative reasoning. Before that was just distributions and we had no context. And quantitative reasoning still falls under that logical reasoning, family of reasoning and arguments, that you have a starting question going down to an actual answer, and you have a systematic sequence of steps that you are going through to reach that actual point. And with quantitative reasoning, you're combining some form of math skills with some kind of context or disciplinary area that you're working with in the real world, and critical thinking to combine these all together to come to some conclusion. So when we're going through a logical sequence of steps of combining previous facts together to come to a final conclusion overall, we're using like our quantitative reasoning of being our skills of math, in this case statistics for us, and the context we're looking at, and our critical thinking of what we understand from the data and how these tools work and how we can combine them together to come to an actual answer. And remember from here is you could just have numbers like we had the distribution before, but the context is everything. So, is 4 followers a lot? Well, if you're on Instagram, no. In an alley, yes. You've seen this before, but I still think it's hilarious. And I think it sums it up really good that the context tells you something different of how to start interpreting the data and how you would react to answering that actual question. Especially if there's some internals that maybe we're all slightly differently, but trying to back your argument up with the actual numbers. So then here it's saying 4 is the actual number. Instagram is a context, and knowing what follower is and be critical from that, well, no, larger numbers are a better thing when you're trying to deal with social media and being an influencer or whatever you're going for. You don't want just 4, you'd want thousands to millions and so forth, and what connections you can actually make. And that's that context. Whereas if you're being followed in an alley and you're being threatened, it's never a good situation, but if you had fewer people following you, that's better than the same exact scenario when you had 4 to 100 people following you and your chances of actually dealing with that. And that's more that matters within the context, and knowing 4 as being that specific number and the decisions you would make of when it's good or bad. So you have to look at the problem, understand that context, understand if small numbers are good or if large numbers are good, and how to combine that together to make some kind of decision. So we will start with a ridiculously simple example of you want to buy something. You do this all the time. If you don't have credit, you don't want to go into debt. So if you're purely with cash, you don't got a credit card, you can only spend what cash you have on hand, then, well, if you're going to go to buy something, then if we're looking at number ranges, like the number that it costs and also your number of how much money you have to spend along a number line, the smallest you'd have is 0. Boom. You expect no money or it costs nothing. And then above there, this could always keep growing. I've stopped it at 100, but I've left the arrow here to indicate that that number range could keep going further and larger from there. And so that gives us a kind of a context and a number spectrum of when making that kind of decision. And you'll be doing it all the time. You know you're using basic math. So say you have an item that you desire to buy. Here, I've got a fluffy unicorn. Whatever you actually desire and find interesting from there, and we'll say it's $67. So we've set a beginning context. You want to buy something. We know that you're only doing it with cash and you can't go negative from this. You can only buy it with that cash. And you know the thing that you'd like to buy is $67. And so that's the beginning part of the context. Then you've got to make a decision of, can I buy it or not, depending upon how much money you actually have. And so let's assume that like right here, I have $55. So that's how much I have within my actual pocket. And most times you'd be like instantly saying like, well, nope, doesn't match up exactly to 67, and so I can't buy it. Because we just know that. You don't have any cash, you don't have any credit, there's no other way to get anything else. Then we know that between $0 in our pocket up to anything less than 67, right here, so even 66.50, you're like, we can't buy it. Maybe if you're other people that are braver than me and you're really, really close, you start haggling with them. And, you know, some of that range here, I haggle if I'm going to make a decision. So this line here will become important. We'll talk about that later on of like, how close is close enough before I make that decision to haggle. If it's down at 0, yeah, I'm not brave enough to start doing that. But we know either way right now we have this kind of range. And we know like, okay, well, 55, 67, I can't afford it. That's a basic argument. If I wanted to state my reasoning using the quantitative reasoning and kind of back it up in a sequence of actual steps, I'd have to start with my premises. One of like, hey, the item costs $67. I have $55. Those are two premises. The next thing that we can combine together is then, okay, well then I can use math to subtract it. And I can say, well, as a third premise, okay, well this is, we'll say that's premise 1, that's premise 2, well then premise 3, and using some quantitative reasoning skills, I know, well, I can subtract those. Because I know if I subtract it and it's 0, I have enough money. If I subtract it and I have a positive number, then I have more money than it's actually needed. Or if I subtract it and I get a negative number from there, depending on how you're doing it. And being a region, maybe I can't actually afford it. And so how far am I off? And like, well, we know that already. If their number lines are good, the 3 is that like, okay, I can subtract it and there's a difference of actually 12. But in this case, what we know is, okay, yeah, fine. 55 is less than 67. That's just an automatic given for what we've learned at this time before. So this is less and it's less by 12. And well, because it's less, I can't actually afford it. And so those premises. So 1 is I have 55. 2 is that it costs $67. 3, if I have less money than it's required for it, I can't buy it. Okay, well, how much is the difference? A difference of $12 and it's less. So combining all these together, I can argument I can't buy it. So knowing, okay, well, bringing this whole thing back together and elaborating what is a very simple concept, but still trying to show the quantitative reasoning and logical sequence of steps is, okay, item costs $67. I have $55. If I have any money less than what's required, I can't buy it. Okay, well, 55 is less than 67 by $12, so therefore I cannot buy it. And here using more quantitative skills because you're saying, okay, the number is just saying 55 is less than 67. That's enough to do it, but also quantifying by saying how much by $12. I mean, that's way too much to start by haggling. So I'd say, well, $12 is too much for me to start haggling, so I can't afford it and I can't buy it, and that's my reasoning for it. And hopefully from there you can see the sequence of steps I went to and not just letting someone else come to a basic decision. Now, this is an easier problem. We get to larger problems. You need to spell out all these steps for why you are coming to your final conclusion. So another example. Okay, well in this case here instead is I've got $90. It costs $67. I know I can subtract the actual 2, a difference of 23, and then we know that 4, a step for the premise right here is that, okay, well, okay, 67 is less than $90. Oops. Boom. Is less than 90. Okay, well, with this then, well, I can start with the argument, okay? Argument 1, or premise 1, is that I have $90. Premise 2 is it costs 67. Premise 4 is, okay, well, 67 is less than 90, which leaves us as $23. So hella yes, I can buy this, and I will be left with $23 after this that I can still spend on other things. So easier. But what if we're at the case where they're really close? So here we got 68. It costs 67. We know that we have a difference of only $1. And well, here still, okay, we still get the case that, okay, well, 67 is less than 68. And so here we're like, okay, 1. It costs 67. 2, I have 68. That's a difference of $1. And 67 is less than 68. So what it costs is less than what I have in my pocket. So I can buy it, but should I? Because I'll only be left with $1 to spend after that. So depends upon the context. But now this range of being this difference and how big that difference is, this 1, is going to become a lot more important later on when we're dealing with the analysis of actual data. And if we're looking at 2 data sets and we see there's not much difference, then maybe our cause and effect isn't actually in play. So this will become more important when we cover statistical significance, and then when we come back to scientific method 3 and we have more problems. So you'll see this pop up again later on, and why I wanted to bring it in here for this example. But let's get to something a little bit bigger, a little bit more of a context, something that you as a student, if you're in university now, you're used to, exam scores. But imagine yourself here. So we'll give a context. Imagine yourself as a teacher for an introductory course such as GNED 1103. There are 84 students in your course. Your class recently completed an exam and you want to evaluate how the class did overall. So did they do good, bad, was it too hard, and something in backing this up by data. Now, okay, well, the exam was out of 200 marks, and the statistics below were based upon the grades each student received. So this is the raw grades. So if they got 150 out of 200 marks, and so forth from there. And we need to just kind of describe what do we see that's happening and back up our argument from it. And this could be open-ended for different people because your argument of where you would say is good and bad is different, but then at least you can quantify that, and you could say things, well, no, I only consider to be between 140 to 200 marks to actually be considered to be good. But in this case, we can look first, okay, well, are smaller numbers better or larger numbers better? And in the case of a test, larger numbers means better scores, percentages overall, people will be doing better in the course, and so larger numbers will be better versus lower numbers down here. And this is why I've brought back this little infographic of the happy smiley faces, of green smiley up at the top being good, and measures going down of shades of green, slightly smiling, to neutral at all, to not really happy, to super not happy, and within this low end. And we need to start describing what do we see from this and in this context. Now, overall, we could quickly go, we know the minimum. The bottom person or people in the class got 5 marks, because there could be 5, but there could be others that are there. And the top person or people in the class got 180 marks on the test. And we know this up here. So, okay, this is good. Okay, well, how is the data actually skewed or not? And so, again, you want to look at if it's normal distribution, well, it's going up from here to 100 marks and then down to 200. And we want to look at the mean, median, and the actual mode. And quickly looking at our diagram, we can see, well, they don't all match up. The mean and median are close together, but once again, we have a mode that's way off as an actual peak, which is actually up here in this Q3, the upper part of the interquartile range. And you're like, okay, this doesn't look good. And the mode is greater than the median, is greater than the mean. And remember, okay, the mean's going down towards the tail, so we probably have a skew with the tail going towards the smaller number, so we're negatively or leftly skewed. And so even trying to quickly draw over top of this, we are probably getting something like this of a skew, somewhat. And so we know that we have more data clumping up within these overall ranges. And so we know here, okay, well, there's a field that, okay, we'll probably have a good chunk of people that are doing not so bad on here, the higher marks for the actual overall test, but no one got 100%. We know that automatically, and we know where the min is, but there is still a wider range. Now, you'll know so far as I've talked very vague, is that if you're giving if I give you this as a question on a future test or task, is you've got to be more specific in quantifying. If you're saying larger, by how much? And you need to back it up from that data. Well, this much of this data falls between these 2 points and so forth. So right now we know we're skewed. We have a feel of where it's going on, and we need to start backing up some of that actual data. So one example is if we were to say, well, no one got 100%, what we can say is well, the max score here was 180, and you needed 200 marks to get 100%. So we can say, no, the highest we have here is 180 overall for everyone in the class, whereas the lowest is actually 5. So no one outright got 0 on the test, but 5 is not a good mark in the scale from 0 to 200. So here now is I've just thrown up a few extra things to remind you again what some of these ranges actually tell you and how you can start backing up more of your argument of what's happening. Is that one is from the median, from right here, is that we know that means that it's a splitting point that 50% of the data goes this way and 50% of the data goes this way. We don't know how it's exactly distributed. We just know that they fall between these points. So from min to the median and from median to the actual max, you know, you have that distribution. Now, we were told before in the context, okay, there's 84 students in the course, and all of our gathered data points that we have is the scores they got. And so that means that, okay, well then 42 of the students fell here, and 42 of the students fell here. So we can start quantifying, saying in the beginning, well, half the class got a score between 5 to 98 marks, and the other half the class got between 98 to 180 marks. And we can even break it down more of knowing, okay, well, within those, we know we've got this quarter range. And again, a quarter of 84 students is 21. And so we know that 21 people fell between 5 and 51 marks, and then another 21 between 51.5 to 98, and then 98 to 141. Like we know what ranges we start having. And we know that we have the mode is up here in this upper range of Q3. And so we know that, okay, well, if mode is 141, that we had a good chunk of spike of students who were getting 141 out of the actual 200. And overall, like, there's some sways of they're kind of doing good, but then there's this chunk of people who are doing below. Like, even on this range, if we say from here, is that 42 people got between 5 and 98. And, you know, we have 100 out of 200. That's halfway in between, so that's almost 50%. So half our class got below 50%, and the other class half got above 50%. And it's a little skewed going above here based upon the actual, we can say, well, okay, the mode median is skewed from here. We know we have the mode up here by the Q3. We know we have max. And so overall, I don't know, like, to me, it's starting to feel like this class overall, it's kind of like some people did good, but some people didn't, and it's not an even distribution. We have a few better cases, but it's more like half the class, so 24 people basically like failed the test or got below that. And then there's a skew that the other half, well, they generally did good, and that there's a peak coming up here more at the actual mode and that difference. And so we can say, well, the upper half of the class, so the lower half of the class, we start saying, well, they got lower marks. And like even splitting between here, it doesn't seem like it's that much difference. That 555 is 45. This is roughly 45. And so in the lower half, they're kind of like distributed evenly. Like if you're looking for those scores, okay, well, they're in between, but that's peak even in here. You're like, no, this isn't working out good. Whereas here, well, this is where we have that upper clump going. So if we then talk about the upper part of the class, is a bunch of them are doing good, but that still only falls within a quarter of the range because they're following between roughly Q3 to max. We know that's 25%. So really only the 25% top of the class did really good. And that's 21 people out of 81. So it's kind of like we have to split the class at the lower end, and something's going on here. Now, in this case, to make it maybe easier to relate to, it's the exact same values that we had here before, but now we are looking at everything's been converted to percents. Something to relate to. So it's the same distribution, and instead here, the number line is then all the numbers were converted to the percent score they would have gotten to. And since it was out of 200, like we know, okay, we can just divide everything by 100. Now, you don't have to do this to back up your argument, but it could be one way to realize to use your critical skills is, okay, maybe compared to seeing these numbers, which is the raw test scores to relate to, it's hard to know exactly. And okay, well, in percentages, it's easier to know how people were actually doing. What does it mean from a 5 to 98 when it's just, okay, we convert everything to percent? So this is more your quantitative and critical reasoning skills coming to play to be like, okay, well, maybe I want to back up my argument by first using the math to convert everything to percent. So you convert everything to percents from right here, and so that's your decision, because you could have gone this other way, made an argument's perfectly fine, or you could decide, okay, I could also convert it to percents and then argue from there, and then maybe it's easier for me to see, because we can say, well, if we're going for percents now of their actual data, and because we can do that because it's a test and this is the context, well, now we know that the bottom half of the class fell between 2.5, so the 50% of the students in the class were like 2.5% to 49%. And you're like, I don't consider that to be good. It's not just passing. Like maybe you're at 50 and you're like, woohoo, just passed. But I would say the line myself that I would personally draw is that at least up here at 60. So now this is my own bias of saying what is good. Some people would be like, nope, gotta be 100, or nope, it's gotta be like 90. That's up to yours. But if I was saying 60 was my choice, and I could state that as okay, my premise, I would consider anything 60 or above is showing something is actually better. And you can see, well, these bottom ranges, everyone was even further, and it's off by here, well, 49 to 60 is off by 11%. You're like, well, no, that's not good. And so I could add that in as a premise of saying, okay, that's my line right there. And so, like, but with the percentages, we can start seeing, okay, half the class got below 49%, and the other half then range from 49% to 90%. And then I can dig down deeper as well, okay, in that lower range of students who failed, well, 21 of them got between 2.5 to 25.51%, and then, like, up from here is 25 to 49, you're like, it's still not even the best. Like, they're distributed across. And, okay, well, if we go to the upper ranges, so we can say now, okay, that lower range, not so good. We can talk more quantified. We could add in our fact of what we think is a good line. Say if mine was 60, and we could say the difference off from there and why we consider that to be bad. But if we look at the second half of the actual data and knowing, look at the spread, we know the median from right here, and we look at this interquartile, we're like, okay, boom, not okay. Well, these net group is going from 49%, so there's a few people on this edge that still failed, but it goes up to 70%, and that's still a difference of roughly like 20. Come over right here, versus, okay, well, same here, it's 20 up here. So these are distributed across, but there's still more that we know, okay, because the mode is up here at Q3, even though this is 25% and this is 25%, across here, there's going to be a peak. And we know that we have more of them coming there due to what the mode is, which is the most frequency of seeing for those actual values. And so we can say the bottom class failed. So like, we're seeing the same thing we saw before, but now in percentages, maybe it's easier to make an argument. Even here, trying to argue stuff more with the spread of like 185 like marks right here, but even the spread of percent from like 2.5 up to 90 being up to 90, you're getting like 89% kind of in your spread of values. But if we look at the interquartile range, maybe it's another way to try making an argument. We can look between this value to this value and talk about that range in relation to the actual median here. And these look roughly equally distributed, the size of the boxes. Well, between Q1 to Q3, we could just subtract those two values from each other, and you'd be getting like roughly 45, and you're like, well, the range is 45 and it's going from lower to higher. So it's like, no, I'm still not seeing anything better. Is that I can say some people did good, but the majority of people either did a middle range from here and a lot more failed and going down from there. So those exam marks are not the best. Okay, well, let's look at another one. So same as before. So same exam, but some different grades, and so we still have 84 students, and the test is still out of 200. And so we can start seeing automatic. If I go back to the previous slide, you're like, okay, no, this was more lower range, and this is more higher range. And well, what's going on? So first thing, look at the skew and seeing which is a better measure of centrality. And from right here, it's hard to see from the whiskers going across through here, but we still see that there is a bigger chunk of data, and these are squashed together, and you have this mode. So we are still getting a skew. And so the median would probably be a better one in this case, again, to use for centrality. And looking at mode and taking that into a context. The difference between these two is not as great. You can see that here, the 128.5, 119, you're off by 10. So we're still pushing it there. So the median is probably still better. We can still have this mode, and so going from max and realizing that this is probably a peak, we're probably getting something like this, and then it's coming down. And we're getting a lot of them up here in this upper cases and versus going downwards from there on the overall marks. And so mode is greater than mean, greater than median and mean, so it's skewed to the left, meaning that we have a lot of data points going towards the right and giving you that kind of range. And we can already automatically see from here that, okay, well, we're getting a lot more clustering happening in this case here. So remember, that's 25% versus this is 25%, and this is 25%. And so we're like, okay, we know that up here we are getting a lot more within this kind of range that's clumping in these upper cases. And even for the median, we can see the higher case, even just looking at the line, is that the clumping between, well, half the class is here and the other half the class is from right here. We can tell a little bit more what's happening. So now, again, overlaying these boxes above just as a reminder to getting those values and calculating them out. Ranges, you don't always have to do this, but sometimes it could help you to visualize and see what's going on. Well, what do we get from here? We're getting, okay, well, again, 84 people, half, and so then that means 42 people go up between 128 to 180 marks. So maybe we got that wrong. So that's 200 marks. It should be because the max is 200. So that's a little mistake on the slide there. And here, so 157 to 200. And like, okay, well, that's doing better. And even at the low end here, well, the min, this time the min is at 26. So we're going at 26. And so from 36, sorry. So from 36 up to 128, we're like, okay, well, that's half the class. We know right here is that kind of passing mark. And so we still have a chunk here that you're like, okay, well, now in this case is that even if we're looking at like from 100 and going here, it looks to me like there would be less data points versus here. So like we already know, okay, well, there's more people that would be passing the exam because you have to get above 50% to be considered a pass, and seeing what's happening from there. So I feel like, okay, yeah, more people are going to be passing. We quantify that by saying, okay, 50%, 100 be here for marking, and we know we have all these ranges, blah, blah, blah. I know I can see what's going on, that more people are passing. We can even see here, if we're going half and get a little bit more specific in our quantities, is even as interquartile, we have 21 people clumping around this range of 128 to 157 marks. And so we know that, okay, we're getting a lot more. And just to make this easier, like probably as an argument, I've also converted these all to percentages again. And this is probably where you will see that, okay, yeah, I can make a better argument, maybe relate to a little bit more in the context for being a percent. And so we know is, well, okay, half the class for the median, and make an argument here, got between 64.25% and 100% on the test. I would say that that's good. If I was still going with my marker that I was considering 60% to be my personal marker for being better for the class, and they got 64, and well, it's a difference of 4%, so they're above that range, and so, hey, they're doing better. I consider that to be okay. Maybe you'd make an argument that 90 should be better and the rest of the class isn't doing good, but that's where you would set that. You would state that in your argument, what you consider that line to be good. So we know, we got this from here, and we can even say clumping these more down. Okay, there's a range, but from 78% to 100, like we're still getting a good amount of students here. So I'd say, like, in these cases, there's not an exact problem or question we're trying to answer, and so that's why I've kind of been talking quick, but I'm trying to give you a feel for how you can start interpreting and pulling more information out, and then start quantifying it in your arguments for how much is there. Because we can say, okay, if it's above 50% here, it's like we know that, okay, well, like from here to here is 50% of the students, so 42 students did good in the course, and giving you a range of that 64 to 100, and how best you decide to make that kind of argument. But we can start telling that from these graphics and start pulling out actual overall data. So now, what if we switch it up a little bit and we add an extra thing that you have to decide from here? So this is the same one we've dealt with before, so same kind of class, same distributions and everything else. But now we've had a new thing, is that you got to talk about the class, and you have to talk about how did you do in relation to the rest of the class. So if we got 150 marks on the actual test, and we have the rest of these graphics, well, now we can start quantifying where do we sit. So we can make our whole argument for how the class was going before by looking at all the actual values, and then we can start deciding, okay, well, where are we? And what we know is, like, well, we're in the upper half of the class, knowing that for the median from right here to here, so we're in the top, like, 42 students of the actual class, and we're not the highest score. And we can say at the top is that, okay, we got 150, and the median, which splits it here, is that within that group we can start calculating, well, what's the difference between the median of 128 and 150 from there, and we can get that number and say, well, we're this much above the median. We can also say, well, we don't fall within the top quarter of the class. So the top 21 people went between here of 200 and here what is Q3, which is, so you have the two, so you have 200 and 157. So we're not in the top, we're in the top 50%, but we're not in the top 25% of the actual class. And now within our group of 25% of the class, so it's 84, so it's 21 students, is that we're most likely near the upper edge because we're here. We have Q3, and now we can start looking at, okay, well, we've got the Q3 value and we've got our score, and we can start comparing the two of those. And well, I'm only 7 marks off from the top, so at least within the quarter students and the top here is I am almost near the top of those students because difference of only 7 marks off within this actual context. So start seeing how you can start pulling out more things to back up your actual data or your argument. And so here, same thing again, but now done into percents, and maybe because the critical thinking, the context of changing it to percents, which could have helped you, you could convert that over and make your argument from there. It's like, well, I'm getting 75%, and I considered 60% to be good, and okay, the top here is 100%, so I'm 25% off from the top actual mark. I'm not in the top amount of the actual course, so 25% here was subtracting 100% from 75. Right there, and then, okay, I'm here, and I can say, okay, I'm off from this top quartile. Okay, well, that's 78%, so I'm only, okay, from 75%, I'm only 3.50% off from the top group that I'm with, but I'm still not at the very top of these actual clusters. So how I can start pulling more information to be critical and drawing up and making my argument and stating from all those facts coming out of it. Now, another thing you can do, and we're definitely going to see this when it comes to analyzing our data after an experiment, where you're going to start learning about statistical significance and having your logical controls and different groups you're gathering data on, is now we can take these different distributions, which would be tons of numbers, 2 different sets, and if they're in the same context of, okay, well, what are they? They're measurements, but maybe one thing was changed from, but everything else is kept the same. We can then start comparing the data. So in this class, we'll imagine we compared both classes. So this is the distributions from both classes. You can see the top data here for that one, and this data here for this one. And these are the two that we're looking at before. And now we have a way to compare the two of these. How are these two classes doing? And having this overlaid, we now can see, like, I'm probably just quickly looking going to guess that this bottom class overall did good. But I want to back up my argument and go through things of like, well, I could look at the min. That's right here. I could look between these two values and I can figure out, okay, well, what's the difference between the two of them? So subtracting that 18% from 2.5 and saying, okay, well, the mins is even bigger from here. And then even at the largest values as the students overall, what's the difference here, and is that large enough? I can then next go to where the modes are, where's the peaks, and see what's the difference between that, and is that large enough for me to care? And here I would say it would. We can then go also, and we can back up even stronger, saying what's the median? And this would help because we know, okay, well, that's 50%, this is 50%, that's 50%, and so we can know here is like, okay, well, even the top area here from like this range, you're like, okay, well, what's the difference here? And even half the class, that there's a big chunk that's moving larger. And then even next, we can start comparing the interquartile ranges and see what the differences are there. So same thing here. And which one's larger in the context, which one says overall. And so even before just trying to make the vague thing that this bottom class did better, we can go through everything and back up an argument to say, is this bigger than this by enough? Is this bigger by this than enough? Same thing for the interquartile ranges, the medians, and so forth, and quantify and say, well, exactly how much is this? And is that big enough to draw a conclusion that the bottom class did better than the overall class? And is it big enough to draw those conclusions? Okay, and so here's another context to give you a feel for where this would come from if we were going into, say, more of a science perspective, where you again have your cause and effect that you're actually looking for, and you're measuring the data. So this one's not perfectly backed up. You don't know everything else in their question, their background research, and so forth for the design, but we can start looking, well, how would we start analyzing the data? So this is, again, coming where we get a little bit of the context, and it's science, and we have to know what's the cause and effect, And you can see here it says, like, an atmospheric chemist wants to know how much an interstate freeway contributes to local air pollution and the health of individuals. And so this is really key of being, okay, well, interstate freeway cause and effect being pollution, which also correlates to the health of the actual individuals. And so we're like, okay, well, how much does interstate affect how much pollution there is, because the pollution affects how much actual health, like the health of individuals automatically, and it's already shown. And so we know we have that first off of being our cause being the freeway and the effect being the pollution, and why we care about this is because the health of individuals. Okay, specifically they want to measure the amount of fine particulate matter, small particles less than 2.5 micrometers in diameter in the air, because this type of pollution has been linked to serious health problems. So what this is saying already is there's already stuff that shows that there's a link or correlation or causation to improve for showing that this type of pollution here has an effect on people's health. And so we know is, okay, well, they're measuring it here, and the more particles you have, the more pollution you have, and that's bad for people's health. And the less particles you have means less pollution, and that's better for people's actual health. And so that's why then we're looking here, if I get like a number scale, and I've just picked these values like arbitrarily, well, should be at least 0, because if it's 0, that means there's no particulate, and there'll be no pollution. There's not going to be negative measurements because there's no particles at all, versus this higher scale, we don't know where that could have been and go larger. But then I'd want to switch this around, where normally we've had happy here and sad down here. But now we're like, okay, well, no, smaller values mean less pollution, so we'd be happier, versus larger values mean, okay, no, unhealthy, unhappy. And we have to know it's part of our context now. When we start analyzing our data, we're worried more if it's going to be clumping down here or here to say what effect happened overall. And so here we have measurements, and what they've done is they've taken it from 10 miles away next. So they're looking at away from the highway, where there shouldn't be any highway and shouldn't be affecting it at all, and taking some measurements to get a base value from right here. So this is the away, this is away from the highway versus this is next to the highway, and measuring the particulate both, and then seeing, well, if we're near the highway and there's more particles overall, maybe the highway's having an effect, versus if we go away from the actual highway and we measure and maybe we're not seeing that same amount of particles at that point. Now, this is not the best designed experiment, but this is just giving you a little bit more context when we're going to the quantitative and statistical reasoning. So, first step, how is the data actually skewed, and which is the better measure of centrality and spread that we should go look at? And so again, you're looking at the actual mode, median, and mean from the rest of these. And we can see from this first one that it's positively left skewed. So again, to me, like being positive skewed, that says that you're getting clumping like this. I should draw that better. Is that you're getting clumping like that. Is that, okay, it's even better. Boom. Is that it's more down here at the lower values versus the higher values most likely, but we don't know yet till we get the rest of these drawn to see what's going on. And if we look here next to the actual highway, it says that it's left skewed. So mode, median, and mean are larger values. So this is saying that you're getting more of a clumping here, and your skewed's coming down here towards this. So we're getting clumping near the higher values. So we have first indication, because the skew is that something is going on. We have to see how different this is. And we need to then draw out our box diagrams, get our descriptive statistics, and combine it all together. And the fact that they're both skewed is that we should probably be using the actual median, and the fact that the median and mean are such far off values from each other, especially in some cases like here next to the high, like, oh, these are like these values from right here, is that probably the median is a better value with these skews to work with. But now if we look at both of these, we can quickly see, okay, well, this is away from the highway and this is next to the highway, and they're both taking the same number of actual measurements overall, and we can see, okay, well, this here is showing that this is clustering more down here versus this is clustering more here. You're like, okay, look, we're away from the highway, we're getting low particulate, better for health. Next to the highway, we're getting more particulate and probably not so good for actual health. And you're like, okay, well, okay, that's good. We know they're clustering. And we can look, okay, what's happening between the max values and what's this difference? And I would say this is probably big enough that we're like, okay, same as like here, what is the actual difference between these two? And you're like, okay, well, that seems to be larger. So even the minimum, like even a minimum next to the highway, it's getting more than like we're saying is the minimum away from it, same as the actual max. Look at the median, you're like, okay, well, 50% of the data. I just clicked ahead. Give me 1 second. And so we know that, okay, well, 50% of the data, I did it again. 50% of the data is here for away from the actual highway versus 50% up here. And same thing from these two things. You're like, okay, half the measurements here between this range of min to median fell within this good range versus if it's here, these ranges are larger. And I can start quantifying by subtracting those two and coming back to this. And so you can see how these descriptive statistics start helping us and how we can start quantifying our answer. We'll get into that more when we get to other examples making that decision. But like I would say as a quick feeling, you're like, yes, next the highway seems to have more of effect, and we can back our argument by, well, how big is this? So we're dealing with that statistical significance thing that we're going to come up to. And this of, okay, well, no, like this is big enough range. I can then start making an argument, backing it up with actual quantity, see how big that difference is. And that you're like, no, it's the highways having more particulate bad for health, the away from the highways not. And so probably we are seeing our cause and effect. And we could analyze then out of this to say accept or reject and back it up by really being specific about these quantities and using these values and these statistical metrics to make our decision. So really showing our quantitative reasoning skills brought together. Okay, so I hope this gave you a better feel. It's only an hour and maybe like 12 minutes or so far. It's not perfect to build it up, and you have to practice and understand, okay, well, really making sure you understand what the median, mean, and mode, and max, and these box and whisker diagrams are showing you and how to start interpreting and pulling numbers out of it. But you can see how it helps us at least analyze stuff quicker from these and pull it from there. But we will have more practice in the actual course from this before we reach the final and the end. So once we get through some more science, I'll be going through some more detailed examples of building up that actual argument, maybe giving you some guidelines of what to follow in the relation for this course, because I know from this course I'm not going to make you perfect for making arguments everywhere else if you take stats courses, but you'll be at a better feel for what to do, and you'll have practiced in that universal mathematic language that's in science as a way to talk using quantified terms and based upon your empirical evidence. And if you're going to engage in that science community, this will become part of like how you have to start speaking and what you do. Okay. And as always, I hope you're all doing good and you've done something good for yourself or someone else during this time, and we can take steps to make this world a better place, no matter how small those steps may be.